Hello class. Today we begin Chapter 9. And Chapter 9 we're going to start working with everything that we've learned up to this point. We've been covering some concepts throughout the first half of the year. Particularly, we've dealt with fundamental operations in Chapter 1. And particularly we learned the order of those operations and how we should multiply, divide, add and subtract, how do we use exponents, parentheses. So we learned a lot there in Chapter 1. And then from Chapters 2 through 8, we've learned different concepts from functions and graphs. We learned about equations. We've learned how to handle exponents. And now as we approach Chapter 9, we're going to start applying all of this as we start really learning algebra. Algebra, though we have learned these particular concepts that are part of algebra and we understand how to use a variable, this is truly where it becomes more applied. We're going to start learning polynomials. And in polynomials, we're going to learn what a monomial is, then we're going to learn what a polynomial is, and basically these are just expressions, and a monomial is an expression of one variable, and then we're going to start working with polynomials, which we start adding and subtracting them. And then we're going to learn how to multiply them, divide them, and then we're going to learn in Chapter 10, this leads all to Chapter 10, where we start doing factoring. And factoring is very important. Factors are basically multiples. When we start multiplying things, we call them factors. When we add them, they're called terms. And factoring is going to be very hard for us if we don't fully comprehend polynomials in this particular chapter. So we're really going to have to put a lot of focus and attention, and it does even continue further as we go into fractions. You'd think fractions are just fractions. Well, we're going to be dealing with variables, and we're also going to be dealing in fractions. We're going to be dealing with polynomials, and we're going to have to learn how to factor them. Similarly, when you have, say, a number and you're dividing, you have a fraction, and you have, say, 500 divided by 100. Well, we already know that that's 5 because we would divide in, but we also know that you have 5 times 100 and 1 times 100, so the hundreds would cancel out and you would end up with 5 over 1. But we're going to need to do the same thing with variables, because with variables you're not going to be able to just divide them as easily. Though we will learn how to divide variables, we will be able to take shortcuts as we go through learning how to use fractions. So let's start with Chapter 9, and we're going to be on, let's see here, we have page number 394. And this lesson is on monomials. And we see here a falling object over here on the left side. And you see this a strobe light. A photograph was taken with a strobe light. Let's read. The falling object does not travel at a steady rate, but moves faster and faster. This photograph taken with the strobe light shows several positions of an apple falling through the air. Although a time interval between each flash of light is the same, the distance covered by the apple becomes larger and larger. Now, so you could see that the time distance between the very top to the first apple, the very top where you see the apple was being dropped, that's the same time, okay? And then you see the next one, and you could see that after the same period of time, it's gone further. Now, we've dealt with this, and we know that we're dealing with an exponent here. We've dealt with this in functions and graphing. But look at what happens now. We see the apple is further and further apart as time goes. Now, a formula relating the distance fallen to the time discovered by Galileo is y is equal to 16 times x squared, in which x is the time in seconds and y is the distance in feet. In the first second, then, the object falls 16 times 1 squared, which is 16 times 1, which is 16 feet. In the first 2 seconds, the object falls 16 times 2 squared, which would then be 16 times 4. Now, you see 1 second went by, but we're going to multiply it by 4 and instead of 1. So We only moved 1 second, but we incremented by 3, and we'll get 64 feet. Actually, if you go further, you're going to notice that you'll have 3 squared, and 3 squared, 16 times 3 squared. Now, 3 squared would be 9, so you went from 1 to 4 to 9, so you could see why the distance is growing, and it's growing exponentially at a rate of time as time elapses. So the expression 16x squared is called a monomial in one variable. So here we have our first definition. A monomial is one variable, say x, all right, is an expression, a monomial in one variable, say x, is an expression of the form a x to the nth power. So we have a form here, all right. Let's get out our trusty little, let's see, we have a times x to the nth power. Okay, now what does this all mean? Well, let's take a look. We see that a is any number, n is a positive integer. All right, and so a could be any number, and n is a positive integer. So this could be any number, but we also read that n, the number a is a coefficient of the monomial. So that's a term that we're learning here, that this is a coefficient. Okay. Sorry, it's very hard to write here. Coefficient. All right. And we also know that the integer n is the degree. Okay, so we have here the degree. Okay, so we have the form a times x to the nth power. Now, if we continue reading, the coefficient of the monomial 16x squared is 16. So the coefficient, we had 16x squared. The coefficient in this place would be, let's go ahead and write the word down. Good. We need to be very cognizant of the math that we're learning, but there are also words that we're learning, so the terminology is important. When you hear of a coefficient, you should know that it is the number next to the variable that is being multiplied. So we see 16 times x squared, so the coefficient, and the degree is equal to 2. Okay, now if we continue on with these other examples, we have x to the 4th power, whose coefficient is 1. Now how is that? Well, we have x to the 4th power. Now, what is a? Well, there is no a, is there? But there's always a 1. We know that. We can always say that's 1. And so our coefficient here is going to be 1, and our degree is going to be 4. Okay, let's take a look at negative 2y to the 9th power. The coefficient is negative 2, and the degree is 9. And 1.5x, whose coefficient is 1.5. Now let's take a look at that one. We have 1.5x. So 1.5 is going to be the coefficient, but then what is the degree? Okay, well we know the degree is 1 because anything to the 1st power is itself, and since there is no degree written here, then we would definitely know that it's just 1. Now let's go back to the top of 395. Notice that according to our definition, 0 is a monomial because 0 is equal to 0 times x to the 1st power. 0 times x to the 2nd power, 0 times x to the 3rd power. Now, because 0 can be written as a monomial of any degree, however, we will not think of it as having a specific degree. So remember, we're talking about degrees, we're talking about the exponent. And so when we think of this number, 0, we know that we can write it many ways. So we have to be very careful. We won't particularly give it a degree. It is useful to define a number by itself, such as 3, or 2 over 5, or negative 8 as a monomial as well. Because a number such as 3 can be written in the form, and now look at this, 3 times x to the 0 power. Well, what do we have here? 3 times 1. And 3 times 1 is equal to 3. Okay, so we can say that it has the degree of 0. Okay, so when you just see a number all by itself, it has a degree of 0. All right. Why? Well, you would say, well, isn't Mr. Cartagena, wouldn't you say that 3 to the first power wouldn't have a degree of 1 because that's equal to 3? Well, that's true. But for us to actually have the monomial, we need to have the x. Okay, this is the form. All right. So if this is the form written as a monomial, we must express it with an x value. And if we're going to express it with an x value, then we need to make sure that that x value does not change the value of our expression of 3. And by doing this, we would have to put x to the 0 power. And we know anything to the 0 power is automatically going to be equal to 1. So now we have 3 times 1, which is equal to 3. So we can express the degree of 3 as 0 as it relates to being a monomial. Okay, so that's what we're talking about. Now, the same reasoning applies to every number. So we will consider the degree of any number except 0 to be 0. Okay, so remember that. It's x to the 0 power because we must write it in the form of ax to the nth power. And for us to write it that way, x would have to be to the 0 power, and that's the degree that we're looking for. We're looking for the degree of the variable, not the degree of the coefficient, okay? Because we know the degree of the coefficient is always going to be equal to 1. In all of these cases, this is 1, this is 1, and this is 1. But that's not what we're interested in. We're interested in the variable. So you're going to have to remember that as you do your problems, and as they ask you questions, you need to be very careful as you read them. Now, let's go on reading here. So we will consider the degree of any number except 0 to be 0. If 2 or more monomials in the same variable have the same degree, their sum or difference can be written as a monomial. So what do we have here? Let's put a new board up here. Okay. Let me get my pen back. Now, let's take a look here. We have 3x plus 4x. All right, and they say that 2 or more monomials in the same variable. So I have the same variable, okay, and the same degree. They have the same degree. This is actually x to the first power. If this is so, then we can write them as a monomial. How do we write them? Well, we would add their coefficients. That would be 3 plus 4 is times x. That would be 3 plus 4, which would be 7, times x. So we have 7x. Let's put this into action. Let's take a look at what we actually have here. What if x were equal to 3? Okay, so we would have 3 times 3 plus 3, 4 times 3. All right. So what do we have? Well, if we were using the distributive rule, we could actually say, there's many ways to look at this. I mean, we're going to solve it the simple way. I'm going to come down here and say this is 9 and this is 12, and 9 plus 12 is equal to 21. Okay. Now, if we were factoring out the distributive rule, we could by using the distributive rule, we have 3 and 3 here, right? So we could actually say what? 3 times 4 plus 3. All right, why? Because this is the reverse of the distributive rule. We factored out the 3. We would have had 3 times 4. Oh, I'm sorry, I wrote this in a reverse order, which could be very confusing. Let's write it in the same order. 3 plus 4. So we would have 3 times 3 plus 3 times 4, which is what we have here. So we could have written it this way. And what's this equal to? Well, 3 times 7. And we know 3 times 7 is equal to 21. So no matter which way we look at this, we could have done it. Now, let's just take a look over here at what we did in this particular section here. What do we have here? Well, we have 7 and we have 3. Now, remember, 3 is x. So going back to what we did up here, we simply added the coefficients 3 and 4. We're doing the same thing right here. We're just adding 3 and 4. And this is 3, which is really, we substituted the x value for 3, right? Or 3 as the x value. So we're basically getting the same answer here. We're getting 3 times 7. Or let's say 7 times 3, right? And remember 3 was x, so that would be the same form. We have 7x. But since we use 3 as the value. So this is the reason why we add the coefficients, because if we were to look at this from the distributive rule, and we could have done that all the way here from the very beginning, we could have said, let's factor out the x and add 3 plus 4, right? The same thing we did down here. This is just the distributive rule going reverse. 3 times x is what we have here, and 4 times x, and we're adding them. So we just changed the form of 3x plus 4x to x times 3 plus 4, and therefore we end up with x times 7, or 7x. Okay, so now if we look at our next group, now one of the things that happens, we start seeing things differently, or at least they're being written differently, but they really are the same. And what I mean by that is we are doing the same math. We just have to be very careful what we do with these monomials. Are they apples to apples? Let's take a look at 6x squared minus x squared. Okay, now we were told that they need to have the same variable and the same degree. Now don't get confused here, because remember we learned the laws of exponents where we were multiplying and dividing, and don't misapply the laws. In this case we're just adding these two variables. As long as they have the same degree and they're the same variable, that means they're both apples. Okay, had this been written as 6x squared minus x to the third power, then I would tell you we have apples and oranges here. We do not have two terms that can actually be simplified. In this case, we can simplify, because as we've learned, we can now take this and we could subtract the 1, which is there's a 1 hidden in there, okay, from the 6, and we end up with 5x squared. So this is really where you're going to have to do a lot of exercises to get comfortable with this, because you're going to lean towards the laws of exponents and should I add the exponents, and you have to be careful that you're not thinking this beyond what you really have here. You're just adding or subtracting, and no different than if this would have been 6x minus x, what would you have written? Oh, that's simple. It's 5x. Now over here they're just simply x squared. Remember, this was x to the first. So we didn't complicate it by putting exponents there, but you got to be very careful that you don't overthink this and say, oh, I remember we are supposed to add, this would be 5x to the fourth power. No, that's not the answer, because we're adding and subtracting. We're not multiplying. So remember how to apply your exponents, the law of exponents. Do not misapply. And the only way that you really learn this is by doing it over and over, and you become familiar with it. Okay, so we have here the answer was 5x squared. Okay, and then we see 2x to the third minus 2x to the third is equal to 0. Well, think about it. 2x to the third, complete, minus 2x to the third, complete. So you're just basically subtracting, and you're going to get 0 because you subtracted something from itself. Okay, so don't allow this complication to confuse you. Now, notice the sum or difference is either a monomial of the same degree or the number is 0. So all of your answers, when you simplify, and that's the term that we're using, and we're going to continue using it more and more, you'll end up with a monomial. If you ever have monomials, or what we call like terms, and those are monomials which are of the same degree, variables having the same degree, and you're adding, subtracting, you must reduce this all the way down. Okay, no different than if you gave me the answer to a problem. Oh, excuse me there. If you gave me the answer to a problem as 6 minus 1, okay, I would say, well, what's the answer? oh, you did all the math and you came down to 6 minus 1. I said, well, why didn't you just give me the answer as 5, okay? Because 6 minus 1 is equal to 5, and you know that. Well, the same thing here. When you have 6x squared minus x squared, the answer is not 6x squared minus x squared. The answer is 5x squared, okay? So just remember, you need to make sure that you simplify all your problems. And you're going to end up with some, as time goes on, you're going to end up with some pretty big polynomials. And you're going to have a bunch of like terms, and you have to be careful that you just put them all together, you subtract them, add them, do whatever you have to, and then express in the simplest terms, okay? Because that's what we're trying to attain with our math. You'd be amazed how you can take some of the ugliest polynomials, and I say that you're going to see it, and I say it in a funny way, because you'll look at this and say, wow, what is this? But when you start breaking it apart into pieces, you're going to start realizing that all you really had there was x, okay? You might say, wow, how could all that big thing actually just be equal to x? Well, we followed factoring. We learned how to handle the polynomials and each of these monomials, and we found that by just simplifying it, we were able to find that it was a very simple answer, or that the expression, not that the answer, but the expression itself was a lot simpler than it really looked. Okay, so let's continue reading. And again, notice that the sum or difference is either a monomial of the same degree or the number 0. Monomials having different degrees cannot be added or subtracted in this way. For example, the sum of x squared and x cubed cannot be written as a monomial. There's no way to write x squared plus x cubed without using an addition sign. So again, let's just take a look what this is. This is a lot different than this. X squared times x cubed. Now you know here, you learned in the previous chapter, oh, these are being multiplied. I can go ahead and just add the exponents. And if you would have done that, you would have gotten an A for the day. Now when you do these two, you might say, oh, I've done that. Well, you really haven't. You thought you've done it. What you did was this. But this is being added. This is being multiplied. You cannot give me this as an answer, okay? You would not have an A for the day, and you'd have a, well, that's really an X meaning wrong, not an X as a variable. It would be wrong, okay? We simply cannot further simplify this, and as they say, it cannot be expressed without using the addition sign, okay? Because what you have here is x times x plus x times x times x, okay? Up here, what you had was x times x times x times x times x. Now you're just multiplying them. Ah, that's x to the 5th power. But this is different. We're not multiplying. At this point, we're adding. And once we add, we can no longer further simplify. So an answer to a problem could look very much like this. X squared plus x cubed. In fact, we'll learn later on that we would write this x cubed plus x squared because we write them in descending degree. Okay, so don't think that your answer is wrong when you see something like this. Say, well, I needed to add these two. I have to simplify it. Mr. Cartagena says that it should just be one monomial. Well, it's not, because these are two different types of monomials that cannot. They're apples and oranges, cannot be added. Okay, let's finish off here. Although the sum or difference of two monomials cannot always be written as another monomial, their product can. So we showed that. For example, using the first law of exponents, we can write x squared times x cubed is equal to x times x squared plus times x cubed is equal to x to the 2 plus 3 power, which is x to the 5th power. In general, the product of two or more monomials is a monomial whose degree is the sum of the degrees of the monomials being multiplied. So remember, we're talking about products here. Products meaning multiplication. And the word factoring is also going to come into that. So you're going to think of these terms. They're all just cousins, dividing, multiplying, products, quotients, factoring. You're going to understand this better as you go further along. We're just going to complicate matters by throwing in that wonderful variable of x in there and maybe even a y or a z as we go along. So we have some examples here. It says here are more examples of how monomials are added and subtracted and multiplied. Now we have if possible, and that now note that they say if possible, meaning maybe it's not possible, so you need to be careful. Before, when you were learning a concept, you knew you just basically had to do what you learned. Now you kind of have different angles to this. Oh, is it this way? Can I do it the other way? Well, you're going to have to know which approach and what you're allowed to do based on the laws and the definitions of all these terms. So, if possible, write the sum of 3x to the fifth plus x to the fifth as a monomial. Okay, so 3x to the fifth plus x to the fifth. Now the first thing we have to see is that we have the same variable. We have the same variable, good. We have the same degree. Okay, that's very good. So we know that this is basically 1x, so we can simply express this as 4x to the fifth. Okay, now if we look at our example, they're going to give us a better explanation. They're going to note that 3x to the fifth is x to the fifth plus x to the fifth plus x to the fifth. And that's true. We could have written this down here. 3x to the fifth is basically x to the fifth plus x to the fifth plus x to the fifth, right? And then we're adding another x to the fifth. So now what do we have? We have 4x to the fifths, right? We have 1, 2, 3, 4. Again, that's 4x to the fifth. They go along and they add the 3 first, and or they show you the example of using the parentheses, but nonetheless, this is what we're doing here. So you got to really be careful with addition and subtraction versus multiplication, particularly, and division, of course. Let's turn over to example number 2 on page 396. If possible, write the difference 2x to the 6 minus x squared as a monomial. Something's fishy here. And we're going to find out what it is. Well, we have the same variable. Okay, checkpoint number 1. We have the same variable. What's our degree? We have 6 here, we have 2 here. Uh-oh. They are not the same degree, so we cannot do anything. It cannot be written as a monomial. Okay, so some things are impossible, and this is one of them. You cannot express this as a monomial. It's going to be written as it is, which is a polynomial. We'll learn more about that in the next lesson. Let's move on to example number 3. Write the product. Okay, now this is getting a little more complicated here. Write the product of 4x to the third power times 6x to the 7th power. Okay. So, big numbers are coming at us here. And if we were to use the method that they're showing, they simply are taking everything and breaking it into little pieces. 4 times x to the third times 6 times x to the 7th. Okay, now we have a tendency of looking at these things sort of as just one whole, it's like one whole piece. And it is, in a sense, we can say that that's a monomial. Okay, but let's be careful that when we're looking at this and when it's being multiplied, that we're not seeing that, well, actually, this is really all one big factor, okay? One big term, rather. And these are many factors within the terms. Factors, or they're being multiplied. So we have 4 times x to the third times 6 times x to the 7th. Now we can group them. And again, we learned this before. We can say, well, let's do 4 times 6 because I can do that, times x to the third times x to the 7th. Now we can go ahead and further simplify by multiplying 4 times 6, and we get 24. And then we have x to the third times x to the 7th. Well, what do? We add the exponents because they're being multiplied, okay? Remember, they're being multiplied, not like up here. Over here, what we were doing, they were being subtracted. If they're being added or subtracted, we cannot apply this the first law. So what do we have? We have x to the 10th power. That's 3 plus 7 is x to the 10th. Okay, and let's look at our last example here. We have write the power 2 or negative 2 x to the 4th raised to the 3rd. Notice how I said that. I mean, you could have said parentheses negative 2x to the fourth end parentheses to the third power. You could say that, or you can just keep raising powers, okay? It's a little tricky. Let's go ahead and do the problem itself. All right, and this is being raised to the third power. Now we want to write this as a monomial. You might say, well, isn't this a monomial already? And I say, well, no, it's not. Because for it to be a monomial, it needs to be ax to the nth. And what I'm seeing here is this being raised to the mth power. If I were to use a variable or a letter here, I'm raising this to a higher. So this is not in the same form. But I know that I can do things here based off of what I've learned. Particularly in chapter 8. And what is it? Well, I know that I can take the negative, I can take this this exponent of 3 and apply it to each the negative 2 and x to the fourth power. So, and those are the factors. So we have to raise each of the factors. So it'll be negative 2 to the third power times x to the fourth power raised to the third power. And what do we get? Well, negative 2 to the third power will be negative 2 times negative 2, which is positive 4, times negative 2 again would be negative 8. Now, x to the fourth power raised to the third power, we know that we multiply here. We don't add them because we're raising it, and we would come up with x to the 12th power. Now we have this written in this monomial form. A times x to the nth power. So now it's written in monomial form. So if you would have told me, hey, that already kind of looks like one of these monomial thingies that you've been telling me, no, it's not even close. You're going to have to do the work and then express it as it's expressed here. Okay, so that is the end of a fairly long lesson, but this is a very fundamental lesson. This is one of the most important lessons that you're going to learn. In fact, this is going to be probably the most important lesson or chapter that you're going to learn in algebra this year is polynomials, because from here on, all of your algebra is going to be based on polynomials and how you handle polynomials. It's not that hard as long as you follow the rules and you do your homework and you do it enough that you become familiar and very comfortable with it.